Hi NeuroTechX, my name is Kaylin.
I'm Han.
And we are MINT, the Multifaceted Innovation and NeuroTechnological team. As a team, we explore possible projects that could impact the neurotechnological field. We are split into 3 sub-teams. The neural and the app dev team work together on the OpenChallenge.
And the electrical team, we work on the big challenge. And today we're going to present to you our most recent accomplishments of our team.
Attention deficit hyperactivity disorder impacts over 6 million children in the US alone, it is estimated. And there are a lot of problems with how it is diagnosed, because it's usually a self-reported assessment, which is very subjective. So we might have problems with both over and under diagnosis. We question ourselves, was there any better way, a more objective way, to assess ADHD? The brain in ADHD is a different brain. It is usually under-aroused, and we can see in this chart, for example, the picture on the right with the EEG, the activity is different on the prefrontal cortex especially. And there are a lot of studies that show a very high correlation between the alpha frequency suppression and the ability to focus in oneself. And so that can also be very related to ADHD conditions, because it usually implies an inability to respond to visual stimuli and an inability to focus.
Hi everyone, my name is Kaylin. As previously mentioned, I'm going to be talking about the process of how we started and went through the project.
Hi, my name is Aloy, and I will be talking you through the code that we wrote and what it means for the mechanisms to work with the Muse headset that will be presented.
So as previously mentioned, the app dev team and the neurological team worked together this year to try and create an app that could aid with treatment and ease of life for people who had the ailment. We did this by using a Muse headset, which is an EEG, which has 4 electrodes. And we realized that if we used a flanker test, which uses a set of cues with a non-targeted and targeted stimuli to create involuntary responses for focus in the brain, we could actually observe those responses and map them using coding. From there, we went through a multitude of tests and did a multitude of amount of data samples using this EEG. We realized that by using the Muse headset and the flanker test in itself, not only could we map the alpha wave, but we could also gain important values such as the dip of the dip depth of the alpha wave, the time spent in the dip, and the number in total for a test.
Hi, I'm going to tell you how we worked on our algorithm for analyzing the data we extract from the Muse. So we first started playing a little with the possible mathematical functions we could be applying to try to see how the alpha suppression was in amplitude and how steep it was. We came up with a numeric derivative algorithm for calculating the derivatives, because MATLAB's num-diff function didn't take the derivative properly for us. So our section data from the graph had some bits in which it wasn't perfectly continuous, and it also wasn't very smooth. So our function that takes the derivative numerically works very well, because the way it does is by first principles. And so after that, we basically saw that we could be calculating the average of the derivatives, and also we could take thresholds of how much we wanted the derivative to pass, so that we could tell how much steep and also theoretically how much the person was focusing at that moment in time. Given that, we could also calculate scores of the average values and also plot everything on a single graph and compare to see if everything was working. We could see that the graph was really matching, the derivatives matched the changes in the graph. And also after doing this, we could also implement this algorithm in a Python code that could run on phones, so that people can use the Muse headsets and automatically get their results whenever they want to use the program on their phones or wherever they would like to use it for their health. Now, talking about the limitations, we added a threshold so we could tell ourselves how steep the derivative was. However, we didn't find any scientific research that was supporting values, for example, that we should be looking for in the derivative values. So we had to use a sample size of people that were tested with the Muse apparatus and check based on that what was more or less visually the average value that we could see the person was starting to focus, and the threshold could be set based on that. The problem was that we didn't have ADHD people to go test our device, so we could also compare both sides of the picture. So for future notice, we should be also looking at how a larger sample size would compare to the average value we could see with a small sample size for the threshold function.
So this year on the app team, in addition to working on the algorithm and adding some more analytics to the results page, we really focused on the usability of the app. So we improved the usability of the app in a couple ways. First, we found that during the flanker test, indicators for if a user had pressed or not would have been very beneficial, so that we added that. We also added a README page to the app itself to explain how to perform the flanker test for any people who are new to it. And we also outputted all the results captured by the Muse headset, so any users who are interested in seeing more of their data can do so.
So right now I'm going to show you how the app works. We have it set up on the phone already. And for the user to use it, they have to have the Muse headset with them. We turn it on. And then set up on our head. On the app, we're going to have a README section if we want to know how to use it and how the flicker test works. And after going over it, the user can just come back to the home section and begin the testing. It scans first to check whether I have the device turned on, and then starts connecting the device to me. And as soon as they are, we're going to see green lights turning on. The user has to put it and let it. And as soon as it's connected, we can just begin the testing. So the user has left and right for buttons to click with the cues, as you can see. And as we go over, all the data is being recorded and transferred to the app on the phone. When we finalize, what we're going to have is the results section. So I'm going to go back. Usually it takes a few minutes, around 4 minutes to run through.
Yeah.
Okay. So they don't look like very good dips, but that's part of the experiment.
Yeah.
Okay. I'm going to look at the control one that we had. We could, with the data we have, run an experiment to try and see if we have the right thing, at least in the compound of it. So like if you section the times of the data that matter.
Yeah.
You add up the raw signal, you average it out.
Yeah.
And then you take the Fourier transform. Find the alpha, does it dip?
Yeah.
You know, like if this was a brain signal and it's just a brain signal that's being overridden by other brain signals on top of it, then we could do that to like average it out and look at it like an ERP.
Yeah.
So like ERPs are event-related potentials. A lot of experiments with ERPs will look at like say you're looking at something when you get surprised. They'll make you surprised multiple times. They'll average out all the bits of time when you were surprised, and then they'll see like a clear signal.
Oh.
Because like each single trial, you have the signal, but it's buried under a lot of noise. The idea is if we treat this like an ERP that's hidden, then we can do that kind of experiment.
As you get down. So if it's not a dip.
What's the point of this though? I don't know. Why do you need like this?
Okay, so
Like why do you have to like make like a new variable and put it?
because if we were to set the values to 0 in the derivative, then later on when we use it for another function, it might read it as 0 instead of the initial derivative value of time.
one of the limitations of the application right now is that data is only captured for the current run, and you aren't able to view the data from like the previous trials. Also, the data, when you want to view the data, you must actually leave the application. It is not currently being embedded within the application's UI. And also the application is quite repetitive and very long, which can lead to the user losing focus, and this can lead to a skew in the final results being incorrect.
Although our testing is not sufficient to conclusively say whether or not the flanker task is an effective method of measurement with using the Muse headset, it was a valid and compelling exploration of what a lifestyle neuroscience product could look like with modern technology.
Hello.
Good.
So like some like ASMR or whatever.
It's filming, it's filming.
Alright, whenever you're ready.
Hi, I'm going to explain how we design our algorithm for a... That sounded very funny. Algorithm. I'm sorry, just continue.